All right, welcome to week 46.1 of Chill Kernel Hacking for Fun. Today is a bonus session. Usually I only stream on Sundays, but today is Monday and I decided to take off work and I'm doing a bit of streaming for fun. And what I want to do is debug the code I wrote yesterday, which is not working. And so we're just going to do a nice chill bonus streaming session. As usual, I'm going to put a test 0 in the chat. And let's get going. So what I'm trying to do is debug why lab or exercise 12 is not working for me. And this is what we saw yesterday. So also let me get my code back up here. Okay. There's a bunch of stuff interesting. Okay. So yes. And what files we were working in? Fork.c, we had dumb fork open. Memlayout.h was important. Yeah, so let's start debugging. So this is what I wrote last time, populate mappings in child. We are working on our user space fork implementation, and the way the user space fork works is the first thing we do is set the user space page fault handler function. We exit fork to a blank process. In the child, we do a little bit of patching up of this one variable. It's a bit of a detail, and then we also need to remember to set the page fault handler for this process also. Welcome to anyone that's joining the chat right now. Thanks for joining. I'm debugging, I'm doing kernel debugging of my, well, debugging my user space fork implementation. Yeah. So this is the function I wrote yesterday. And let's just do a quick git check. So, and here is the code. I did a couple bug fixes. Okay, this is my yes. Okay, so so here's what I'm supposed to see. We're running this fork tree program. It should produce the following messages with interspersed new end, free end, and graceful exit messages. We are not seeing that. All we're seeing is the first one, I am empty string. Probably it's a good time to look at the actual program that we're running. And yeah, so the fork tree function does what? It takes an empty string. Yo, Lizard, what is up? Welcome, good to see you. Welcome to the bonus session. Yes, so fork tree takes an empty string. It prints out I am the string, and it also prints out the environment number. And then it calls fork child with two different things. And what does fork child do? It also passes the current string. Fork child, this is some kind of recursive thing. Fork child takes a string and an extra string to append or something, and it has a certain buffer length. It allocates a buffer if the length of the current string is greater or equal to depth, it returns. Otherwise, it renders this string into the buffer and concatenates these two things, and then calls fork. Maybe it's a good time to get the Miro out just in case. Is 46.1. Good luck with the boring exams. Yeah, I guess it's the end of the semester. I am debugging right now. So yesterday on the stream, I was working on my fork implementation, which is what we're doing in exercise 12. We're implementing like forking processes. But the interesting thing about how it works in this course is it's done from userspace. And so it's not a system call. It's a library call. And there's a bunch of code to write to implement this userspace version of fork. And I did that, or I tried to do that, and it's not working. And so it's time to do some hardcore debugging to see why that's not working. So, as usual, in order to debug it, I need to understand it better, like what it should be doing. So this is clearly some kind of a recursive thing. It starts off with fork tree, and we also have the reference text. I'm just going to pull that up. Copy that into here. Hey Shiv, thanks for joining. What reference you use? I'm going to link you to the course that I'm following. Yes, so what is it saying? I am empty string is the first message we see. Makes sense. Then we recurse into fork child, and we concatenate a 0 onto this. The interesting thing here is what happens. We call fork, and then if we are the child, we then recurse on fork tree and pass this concatenated thing. But if we are not the child, we return. Thanks Lizard. Good luck also with your exams. Yeah, I also have a bunch of resources, Shiv. I will link you to them. I haven't read any of those textbooks in the resources except for the Linux programming interface, but these are ones I've heard are good. So after fork child, if we fork, and then if we're not the child, we actually return from the function, which causes us to hit the second fork child. which then does this whole one thing. So I'm 1, I am 1, 0. 100, oh, interesting. So what I'm a little bit unsure about is this is the given output, but it's saying the messages may not appear in this order, because after we call fork. I'm trying to remember when we hit the scheduler, actually. When a process, I guess it has to be when a process exits. We're not doing any yielding here. Currently, there's no preemptive multitasking. There's only cooperative multitasking. So I don't see any yields here, actually. So that should make it a little bit more deterministic, I think. Yeah. But okay, I would find it helpful just to map this out and just draw this out a little bit. So we start off with the empty string. For some reason, the smoothness of the text is kind of bad today. Okay, I'm gonna restart Miro, I guess. Let me restart. I wonder, I think that helped, actually. Yeah, okay, so that appeared to help. So we start off with this thing. Maybe I will make this half. Can I make this smaller? Apparently not, okay. And I kind of want to make this smaller too. So we call fork tree. Then fork child cur 0. These two things get queued up, basically. And I'm going to try to represent this as a tree because I kind of feel like that's what's happening. So 0 and 1, but first we go into 0. And what happens here? We then compute the string this. And then we call fork. And then parent child, right? So then we have two things here with the parent and the child. And if we are the child, we call fork tree this. And if we're the parent, as far as this is concerned, we kind of finish, and then things go over here. I can maybe represent this with an arrow over here, which I can maybe send to the back. And what does fork tree 0 do? Let's see, sorry, getting some texts. So then fork tree 0 does a similar thing. It prints out I'm at 0. Actually, kind of what I want to kind of figure out is, like, let's ignore this second 1. So let's take a look at fork a bit closer. So when fork executes, it runs all of this code. And the question is, which one gets scheduled? It's not determined here. All that happens here is we allocate a new environment, a new not runnable environment, right? So actually, I think the only time things get rescheduled is when processes exit. Yes, I think that's the only time processes get rescheduled here, because there's no explicit yield calls. And with fork, it creates the new process, but it can't run. The child is frozen until the parent marks it as runnable, but that simply marks it as runnable. It doesn't cause it to run. So then the parent returns, actually. I'm pretty sure the parent returns and gets execution first. So what that means is actually then, but if we kind of map out our process table, it's going to be process 0, and then, or maybe I'll just do it in terms of, so in terms of the order of things, we'll have process this thing, then this process will get queued up. It's the process that's going to call fork tree with this. It's like 1 will get queued up. And things explicitly exit. The child explicitly exits. So with our scheduler, though, it's just a round robin scheduler that's going to choose the next available thing. So for example, what's going to happen is the fork's going to happen. It's going to create another process which will later house this appended string. The parent's going to return actually and hit fork child actually, which is going to do a similar thing but with a 1, and it's going to create this 1 string cause the parent is actually, so the parent kind of forks itself once, and then it forks itself again, actually. So the parent has created 2 children at this point, both of which are going to be in a runnable state, but have not started to run yet. And then I think the parent is actually going to exit. So that is my current understanding. Hey Sparky, is the class going through OCW? No, actually. I am not participating in any kind of organized class. I'm just doing the course materials on my own. I think OCW stands for Open Courseware, right? Yeah, I'm just doing this on my own for no credit, just for knowledge. Yeah, so so that's my kind of understanding. The parent's going to actually exit, and that's the point at which the child is going to get execution. The first child, it's this 0, 1. And only then is it going to print, hi, I am 0. And then we kind of begin this process again, which is interesting. I'll kind of follow that through. So now we called fork tree on this, and we kind of begin the whole thing again. And fork tree takes the given input, and then basically it does this whole thing and appends two things. So it's going to have 0, 0, and 0, 1 will be appended, I believe, because the child's going to fork this one and this one, because we're going to enter here, we're going to enter here. And every time fork tree is called, it triggers the forking of 2 children. Yeah, the 0 and the 1 child. But my understanding is that we're just going to go through these kind of linearly, but maybe I am wrong, because the 1 message only happens later. But maybe it's this kind of depth. It seems like it's this kind of depth first thing. So the first process exits, a rescheduling happens. The next one is picked, running it, and we fork 1 child, which then is created, and by the time we're done with fork, it is runnable, but not running yet. We exit and we queue this second one and we append a 1. And we do the same thing. We queue these up ready to go. And then yeah, so I'm not understanding something. So under my current understanding, we would proceed through these linearly. Every time one process dies, we are going to pick up the next process. And just go through these like this, which would mean that I think the 1 would go next, unless I got this wrong somehow, because wait a sec, so parent forks 1 child, leaves it there. But no, yeah, the parent reaches fork child 1 before this 0 thing gets a chance to execute. So that's why I believe this one will get printed next. Interesting. So, So then maybe we can start to see what is actually happening. So print this. I need to comment out this current feature succeeded. I need to comment this out. These are some of my debug prints. Let's just check this EEBFD. I think that's the stack. Yes. That is the normal user stack. Yes. So we got all these are the expected page faults. But then there's this user fault. Okay, but I think it's actually just time to just step through this. Now, I'm not, or I maybe could add a bit more logging to see what's going on. I might do that first. Time to add a ton of logging. They'll be inspired by this. Pre-populate. Okay, and then we didn't even get to the end. Okay, so maybe I could add some more assertions also. UX stack and dupe page. Rewrite or cal page detected. E B F E. So yeah, maybe it's time to also print out just processing page, add page v adder. This might print a lot of stuff out. Actually, no, not yet. So processing page, this thing, and then we user fault. Then we user fault on the next page after that. Which address, hey Shiv, which address locations are these? If you're talking about these addresses, these are the addresses that, these are the addresses of the pages that are in use by a user space program. It's like the binary there's this one page for like some debugging data, I think, and then this is the stack. So we're here. Got a user fault. I'm doing a bit of print debugging right now. So, okay, yeah, so I think it's right here. Is the panic working again? User panic. Unknown, great. And if we move the panic down, still, are we hitting the fail? Oh, wait, that was kind of dumb. Okay. Okay, I think it's actually time to try using the debugger. How do I debug? Yes, run blah gdb. File object user look tree. Yes. And I want to break on fork, probably. Okay, so here we are in fork. Oh. Right. Okay, so I think now we're here again. I just wanted to go next, but that breaks the debugging. So I can't go next beyond that, which kind of is unfortunate. Okay. So I guess I'll restart. Okay. And then what? I'm going to break on popu. Oh shit. Wow, there's no or wait, no, I file okay, this is going to be annoying them. Let's try this one more time. Debugging. Is this not? Ah, it's it echoed. I'm just gonna copy. Okay. There we go. Fork, so I'll just do both. So now we're here in fork. I'm going to continue. Now we're at populate mappings in child. And what do I want to do? So we are seeing it. There's a specific page where things start to go wrong. I am going to just add if page vadder equals I'm just adding a line which I can put a breakpoint on. Populate mappings in child. And fork.c 204. Oops. Continue fork. And now we're here. We are now processing this page, which has historically caused a bunch of problems. I'm going to step in. Is this really the PTE? This looks weird. That does not. This is how all these PTEs are looking. And I am kind of suspicious about that. I don't really think this is how PTEs are supposed to look. Maybe they are. So how does this work again? So we're seeing a 7, which might make sense. It would be nice to have some way to confirm that this is correct. I wonder how I can do that. Maybe the kernel monitor. All right, so the way these permissions work, it's like, I actually kind of forget. Is it 1? I think you loosen the permissions by adding 1s. So a 1 here means writable, and a 1 here means it's user mode enabled. Is that how this works? Zero is the strictest version, writes are not allowed. then yeah. If 0, user mode is a, so that makes sense for this thing to be a 7 actually, because these pages this page is present, writable, and user mode enabled. Then we have a 6, which means like the page is dirty and accessed, I suppose. Then we have a 0. And then we have the address of a frame. And let me just do a quick check. So we take that, shift it down to 12. Yes. Okay, that was kind of stupid. Okay. So something is already looking kind of wrong. This does not look right. The page, Yeah, before kind of jumping into this, we need to make sure these primitive operations are working correctly. And I'm not sure they are. So I'm like looping through all this stuff. And I thought I looked up the page PTE. But wait a sec, I think it. So what I'm actually going to maybe do is do a print here. The thing that makes me think it was actually sort of being correct is that we are actually only we're getting these print messages on the correct pages, it looks like. What I want to do is look at fork tree now. Do we have any read-only? This 8020 thing is read-only, actually. And we're not seeing it here, actually. This is weird. So yeah, I am having some. Oh wait, no. Okay, the reason these look weird is because they point to physical addresses. That's why. That's why the PTE is not going to contain this 802 thing. It's because the page table entry actually has a physical address in it, and this is a virtual address. So this actually might possibly be correct. But there, oh, wait a sec. It's populate mappings and child thing. No, this dupe page. read only, so we never saw this message. Read only and not cow page detected. We didn't see this, but I think we should have seen this because like the 800,000 page is read, it's not writable. I actually think this might be a bug in the elf loader, which goes back kind of a long time ago, but the permissions are ignored. That's why. So I'm just gonna take some screenshots. So our elf loader was never actually finished. It never interprets the permissions bits, and actually by default it just ignores that, and then all memory becomes writable, I think. Yes, here it is. Every single thing gets allocated as writable, regardless of whether that's correct or not. So maybe that's pretty easy to fix. Maybe it's as easy as int perm equals, I actually, flags. Here is the part where I actually don't know. Here we go. Elf prog flag, right. If it is, then it's PTE write, PTE read. Or no, it's just and region alloc does what? Takes the perm, automatically puts in the we're also poisoning the allocations, unfortunately, but maybe that's okay. Take the perm, when we page insert, we're probably going to add a present bit anyway. Yes. So we don't need to worry about that. So I think something like this is the patch. For basic interpretation of the permissions bits in the binary, we just do a super simple kind of dumb check to see if there is a writable bit. And then if so, we ask for it to be writable. Now, I mean, this is not a bug going to fix the bug, but now it's going to be a bit closer to my expectations. I guess I'll just start GDB again. Ooh. Okay, maybe never mind. What is trap? Let's see, 290. Yeah, I think that's because of the memory poisoning, actually. We allocated So now we're allocating some unwritable memory. But actually this thing, I'm just going to comment this out just in case. I don't actually think this is the problem because it checks if the memory is writable before poisoning it. Okay, you know what? I am actually not going to try to do this right now. That's complicating things more than I wanted to. So I'm going to come back here and get things back at least into the state I had them. Okay. So that actually matched what I was thinking. I forgot to make this hex. But yeah. So this actually does seem to be working, I think. So I'm going to uncomment this. I'll actually just move it down. This output is getting kind of noisy though. All right, maybe not. So back to what we were investigating originally though, which is this user fault. On this EB, it's the page right after the stack, right? And it looks like someone attempted to read or write it. Which is pretty unusual. I want to check what does the error code look like again? Yes, when a page fault happens, the error code is this thing, and it has a couple bits at the bottom that gives information, non-present page, or protection violation. The cause, and this is interpreted here. So it's 4, which means these two. So it was a non-present page. It was a write. It was a write to a read only. Wait. Oh, sorry. 4 is just a single bit. So it was a read from a non-present page in user mode. So why were we, what's up with this read? How were we doing a read like this? It happens. Okay, maybe time to just step through this again. Oh wait, what happened? Oh, I didn't do the GDB thing, okay. Now we're on the temp. Now we're going into what's page vadder is, wait a second. But we don't, okay, so that's this thing, or PTE step. Okay, I've got this. We're doing the system call to, that's what did it. Something there. In this sys page map triggered a page fault. That's so strange. Very strange. Let's just see that one more time. Continue, continue, continue. Step. So this is the stack, right? Let's see both. And then as soon as we do this call, it does the page fault. Next, hits the page fault. Why did that happen? Okay, but at least that's a bit of a hint. So sys page map. Okay, but yeah, like what? No, I need the GDB. How do we look further into this? So here we are, right on the edge. What if we do a step? If we do another step. Now I want to step into the kernel. And going to do this, and I'm going to break sys page map, right? I'm gonna do this, but I'm also just gonna break on trap, I think. And now we're in trap, and now we're entering the system call. Kernel. So now, okay, at least we are entering the system call. It says page map. We should get to sys page map is where we are. This was that thing I was always unsure if it would ever work, but the kind of strange thing though is actually, what? because now we're in the kernel, and it is possible for the kernel to trigger a page fault accidentally. Well, no. If the kernel was the one to trigger a page fault, it would be a panic. That case is caught with a panic, actually. So, I don't think it's possible that the kernel caused the page fault. It has to be user space somehow. That part is kind of a mystery. Okay. So, but let's still just take a look at what this thing does in this page map, right? Looks up environment of both things. Well, let's just keep following along closely. Being kind of squeezed here. Maybe I should have my read elf output over here on the right. That would free up a bit more space. So look up the page info. And here's the part where we insert perm is optimized out. Too bad. All my variables are optimized out. That is so tragic. Okay. And I cannot simply reduce optimization level because the kernel doesn't boot. If I do that, and I have never debugged that for going on like 9 months now, I've just not debugged why that is the case. Okay, but whatever, we are returning from the system call. And I think I'm going to switch back to this symbol table and actually what I want to do, I'm going to exit out of this. Obj user fork tree as. I want to break page map. I want to break pretty early on the return, like something like right here or so. And I'm going to continue. So I'm confident that I think that system call worked. I didn't actually fully verify it, but I'm confident that it's not causing this user space page fault that's crashing things. So now I'm broken in the kernel, but I want to break point again as early as possible when we get back into user space. And I think this is the address, basically, this FO4 thing. It's not, I could probably break even earlier in the system call function, but I don't think I need to. But that breakpoint never even got hit. That is really interesting. Okay, So let's run this all one more time. I should really break point a bit more precisely here. Page map. Page map works, right? Wait, no, there's two page maps. So what I want to do is I want to step as close as possible. Basically, yeah. I want to break syscall, and now we're there. Okay, now things stop. Text 30, I guess. Now I think I accidentally. So now we're in the kernel. Okay, yeah. And my symbols don't work, but that's okay. I'm just going to break. I'm gonna break point right here, which is this call. So with this check thing, so I'm gonna break directly right after the interrupt. And we're there. And so one of these instructions, wait a sec, why? Okay, I kind of messed it up. I think did this thing change? Yeah. Now it's 205 again. No, I really should just break closer to it. This thing, it's really just line 129. Oh, but yeah, I can't directly. So now we're on 129. And now I want to break on this thing. And we're on the interrupt, and I want to break. Or maybe I can just do a next instruction. I'm going to try that. So disaster pointed right at the interrupt. I'm just going to do a next instruction. It seems like that did not work. I need to now set a breakpoint. Oops. So now we are here. We've just returned. And we are working our way through the final instructions here. And I'm just watching for, okay, now we're back in sys page map. We're returning from sys page map. So we did the syscall correctly. And now we're back in dupe page. Was there? And I don't think there's going to be anything here. Is this it? Is it the C printf? If I do a next, no. Oh, now we're hitting this breakpoint again. I'm gonna disable these. Oof. So I want to breakpoint here. No, here. After the call to C printf. Okay. Wow. Okay. Yeah. So, but wait a second. No. Okay. That was good. Why is it here? Okay. Let's try that. Sorry. One more time. This temp thing. I thought I hit the temp. But wait a sec. It's. Okay, now we're primed and at the right spot now. Sorry, this is taking kind of a long time. First one succeeds. Okay, here we go. Time to very precisely breakpoint after the system call. And now we're in the system call. Wait, but didn't I tell it? Here we are. We're after the system call, and we're stepping through the return of the syscall function. Syspage. Ooh. What just happened? That was strange. Okay. So we're broken in the page fault handler, which is not where I want to be. Well, this means it happened. Or did it? Wait a sec, what? The mem move. Okay, but something was so strange there. The page fault function actually got hit. And then it seemed like on the mem move. But I feel like I was getting closer. Okay. Okay, let's start over. So I'm broken out line 205, which is this specific breakpoint for the stack page. We're now there. So this is PTE writable. Trigger this print. I want to step into this page map, which immediately calls into return syscall. I'm going to do a next, and that did it. So that's kind of what I already knew. So let's run this again. .205. Now I'm going to do a step instruction. Calls this page map, step instruction. We're in this page map. This, okay, interesting. I'm going to do a next instruction to skip over this, which already did it. So it seems as if it's really inside the syscall function. It's the first one. Breaks syscall. Continue. So now we're at syscall. And here's that part where I kind of didn't want to do that. At really? So here we are. Now we're there. This thing is completely primed. This does not make any sense. Reds. But why does it say sys page alloc? Am I really being stupid? There's no sys page alloc here. But however, I'm somehow at this EIP. Weird. Why am I at sys page alloc? Ismail, what's up? I am struggling with some debugging as usual. Wow, this is hard. This was so strange. Rewrite or cow page detected. Right? Dupe page, blah, blah, blah. I was in sys page map. I entered the system call function. I returned from the system call function. Wait a sec, but it seems like then it hit this page alloc. But maybe that's because we're somehow already here in the page fault function. So maybe somehow I was attempting to break on the return of sys page map. And it seems like that somehow didn't work. And instead, no. Instead, it seems to have broken on this other thing. It seems to have like triggered the userspace page fault handler and now broke on the first sys call it was making. And if we return, now we're in sys page fault. What this is telling me to do is that I need to break on a few more things. So strange, but I think so continue. So we're here on line yeah, 205. Oops. Kernel. Oops. I also kind of want to break on the place where we invoke the user space trap handler, page font handler. Which is trap.c 362. Yeah. Something like right here. I don't know. Oh, I can't. Okay. Okay. However, we're right here. Is that where I stopped? No, I can go a little bit further, I think. So we get that message. We do the first call. So now we're on the second one. I want to break on two things. That one and that one. So first, we are directly on the int hex30 instruction. And I want to continue, and now we're directly on the one after. Good, so the system call has just finished. And there is something that happens. What just happened there? It seems like we just entered the kernel there somehow. Which is so strange. I just tried to execute one instruction. No, this is not gonna work. We hit breakpoint at DD8. Right. Oh, wait a sec. That's what happened. Wow, that's wild. Okay, that's what happened. So the parent process in our fork implementation, we map the page in the child process as not writable and cow. Then we map ourselves as not writable and cow. And in particular, we are mapping our own stack as not writable with this system call. Guess what the first instruction after the int3 attempts to do? It writes to the stack. which is going to trigger a page fault because we literally just did a system call that made our own stack not writable. I didn't expect that to happen so soon, but like literally you can't go very long without copy on write stack. Like that's going to get paged in very quickly. Wow. So yeah, in the parent process, literally as soon as the system call returns from the int instruction, we execute an instruction that moves the return value of the system call onto the stack and writes to the stack, which causes a page fault, which is now going to fault in the stack. And that's what seems to be crashing. So now if I continue my debugging, I'm in page faults, right? And this is supposed to happen. I wrote to my stack, and now it's time to like actually allocate a proper writable stack and kind of undo the copy on write fault in a stack frame, stack page. And what seems to be happening, a bunch of stuff happens. Oh man. So we just returned from this page alloc. And apparently now it's time to mem move. Oh, wait a sec, but adder. This is the, I see, adder is the address that caused the page fault, but it's not necessarily page aligned, I think. Yeah, here's the bug. Adder is not necessarily page aligned. We can even see what adder is. It's going to be not page aligned, I guarantee you. Yeah, I need to rename the series to Chill Kernel Debugging. That is so true. That is so true. Oh man, I'm trying to be a bit hopeful that I can eventually write some code one day, but I don't. That's the bug. All right, did everyone get that? Like, I'm going to try to quickly sketch it out. So we have our parent process and we have our stack, and we have some other memory, like for the program. And now what we're doing is we are making our child process, and we're going through each mapping and being like, okay, we're going to make both of them read only, and they're going to all point to this common like physical memory. We're doing the same thing with the stack. We have the stack here, like, okay, we're making it read only, and the stack is backed by some common stack memory. So these things point here, and this thing points here. Then, as soon as we do the system call to do this, the parent process returns from the system call and tries to write the return value of the system call into its stack, which triggers a page fault because this thing is we've literally just made it read only. This is going to cause our page fault handler to run, which is right here. And the job And the page fault handler gets a few things it gets, but it gets an address of where the fault happens. And crucially, the address is like not perfectly aligned on a page. The address is like some random place within the mapping. Let's say this block is one page. This place is not aligned. It's like in some random place. And so what we're doing is we're now allocating we're allocating a temporary page in the process. Let's say it's like up here. We're allocating a temporary page and it's writable. We try to copy from the address that faulted into the temporary zone. But the issue is that, let's say this is actually up here, it's not aligned. And so we try to copy a whole like page size from this address line, and we actually go past the boundary. We like overflow and like go off, start copying off the end of the page. And that triggers the page fault that kills us. Yes, that triggers the page fault that kills things when it hits the first out of bounds address after the stack, which is this address. And so what I need to do is I need to be really careful to round this address down. Equals round down uint pointer t adder page size, and this is the address I need to use for like here. So now we allocate the memory, we copy from the aligned address into the temporary zone. And then we map this temporary page to then be mapped onto the aligned address. And then unmap the temporary page. Wow. Okay. That was crazy. Let's try to run this thing. Okay. What is the problem? Oh, do I what is round down? Avoid. Okay, do I not need this? Dang, okay, well that's okay. There are other bugs, it seems. But I think that actually did fix the initial bug though. Now we are successfully processing and doing dupe page on the stack. Yeah, processing page. Exiting gracefully. Okay. So I made progress. Like it's still not working fully, but I actually did just solve the first bug just now. What's happening now is previously our fork was making the child and going through all these mappings and trying to make the read-only versions of them to do the copy on write. And it was crashing when it was crashing when we tried to do a copy on write version of the stack, and we did not make any progress. Now what's happening is we actually do finish. We actually finish the fork, and we do make these two cloned processes where everything is read-only with copy and write. The parent process actually exits. It finishes the fork and exits gracefully. Interesting. Okay, here's what we're seeing. So because the parent process, so here's where we need to look at the actual program running. The parent process does two forks. It does one fork here in this fork shell call, and then it does a second fork. So let's see what we're seeing. So the parent process prints this. It then calls fork. It then does all these messages and finishes fork, right? So that was the first fork. Then we see it return and go into the second fork child. It then does a second fork. It creates a new process, 102, and does all of these messages. Then the parent process has nothing left to do and dies. Exits gracefully. Then it's time to start running the next process, which is going to be the first child. And apparently that like immediately triggers a page fault that kills it. And then apparently the exact same thing happens to the other child. So Ismail, you couldn't even fork before. No, there was no fork at all in the OS. Like I'm doing the first version of it right now. Yeah, like before this, processes were just not able to create other processes at all. The only processes that could exist on the system were those that were like hard coded into the OS to get scheduled. But yeah, so it seems like these things are crashing because, and it's also on the stack. EEBFD is the stack. And for some reason, that's happening. And so, yeah, cool. I'm out of time. So I'm gonna stop here, but I feel pretty good for debugging that first bug. I'm gonna plug myself. Feel free to join the Discord. Please subscribe to my channel if you like what I'm doing. And thanks for joining this extra bonus episode this Monday. I'll be back like usual on Sunday. Have a nice week, and I'll see you later. And thanks, Ismail, for joining. See ya. Bye.